Alright, today we're going to do problem 36 about a circular disk. This circular disk is uniformly charged and the central axis Z is perpendicular to the disk face, with the origin at the disk, meaning that Z is equal to 0 here at the disk. Now, the second figure here is going to give us the magnitude of the electric field along the Z-axis. So at different points along the Z-axis, this tells us what the electric field is. Notice that it decreases, of course, as you get further away. So this maximum value, E sub m, is the value of the magnitude of the electric field when you're at the surface, when Z equals 0. So there's a scale here, Z sub s, the maximum value shown, is equal to 8 centimeters, and our goal is to find the radius of the disk. All right, so we're going to move on to start with, oops, here we go. Let's see, where's the top of the paper? There it is. So we're going to start by drawing a picture of the disk here. This, of course, is one of my disks, so it's an impressionistic disk, as you can clearly see. See the Z-axis. And we would like to know what is the electric field at this point here. So what we're going to do is consider the disk as a whole bunch of little charges and then add the contribution of each little charge to the electric field to find the total electric field. So let's consider a small charge here, which I am going to call dq. So dq is some distance away from the point that I wish to know the electric field at. So I'm going to draw that line here. And this is a distance r. It points towards the point to the x-axis where we're interested in finding the electric field. And it creates a small electric field. We're going to have it point away from the little charge that we're interested in, because if it's positive, if this little charge here is positive, then the field will point away. If the charge is negative, then this will be pointing in the opposite direction automatically, because there will be a negative sign here in dq. So let's call this dE. So this is a small vector, little part of the electric field. And so we say to ourselves that this is kind of a mess, because as we add the different electric fields, they're all going to be pointing different directions, and that's going to be a pain. So let's consider also a little bit of charge on the opposite side. It's the same amount, dq, and it's the same distance away, exactly on the opposite side of the axis. So it's also some distance r away, and it also contributes to the electric field by some amount dE. So notice that because they have the same amount of charge and they're the same distance away from the point, that these two dE values, the magnitude is going to be the same. So the magnitude of dE green will be the same as the magnitude of dE pink. So this is very useful. Let's look at an enlarged version of this part of the graph. So I'm going to bring it down a little bit. We'll again draw the Z-axis, and I'm going to make it much larger so that we will be able to see things. All right, here is the pink one. And then about the same angle. Okay, approximately the same angle is the green. That's a terrible picture. Let's make a different one. When I draw bad pictures, I just like to start over. Okay. So let's start here. Drawing the green one. And then also drawing the pink. Now these two angles here are supposed to be the same. I'm going to call this angle theta. So notice that our pink vector has a part that is parallel to our z-axis and also a component that's perpendicular. The green vector also has a part that is parallel and perpendicular to the z-axis. But the two parts that are perpendicular are exactly pointing opposite directions, so they cancel. This, of course, makes us happy. So that means that the magnitude of the little dE vector here, and there's this part, which I'm going to call dEz. So dEz is equal to the magnitude of the little electric field times, from that single component, times the cosine of theta. Now, if we go back to our original drawing, not this ugly one here, our original drawing, we see that this angle theta is the same as this angle theta down here. So this is a distance z. That means that cosine theta is equal to z over r. Now, next we need to know what is r. Now, r is going to be, we can use Pythagorean's theorem if we know how far this distance is here. Now, this is a radius, so just to keep it clear, I'm going to call it a wee script r. So r squared is equal to z squared plus r squared. So now let's find the electric field due to this little point charge dq. The electric field will be dEz, which is dE vector, its magnitude, times cosine theta. This is a point charge. It's a little bit of charge, so we can treat it like a point. That means the magnitude of the electric field is 1 over 4 pi epsilon naught times the charge dq over the distance squared times, then of course, our cosine theta. Now remember, we don't need the r hat because we're looking only at the magnitude at this point. And r hat has a magnitude of 1. It's a unit vector. So let's write this down again. 1 over 4 pi epsilon naught dq over r squared. And now cosine I can write as z over r. Allow me to write this one last time here as 1 over 4 pi epsilon naught dq times z over r cubed. Now I can write r in terms of z and the script r, so this becomes 1 over 4 pi epsilon naught z over z squared plus r squared to the 3/2 dq. All right, and now we're back. Whoops, excuse me. Let's try making this a little bit bigger so we can read it a little bit better. All right. Here we have our DEZ due to the charge. Now, if I want to find out the total electric field, I need to add up all of the little components. So that means that I will integrate over both sides, because that's all the integral is just adding up a whole bunch of different components. So now we look at this and we say, okay, this looks like fun, but I can't integrate over dq. That doesn't make any sense. But remember that the charge was uniformly spread over the disk. That meant that sigma, charge per area, is equal to a constant. So we could have any charge over any area. Well, the charge over any particular area is a constant. So that means even if I had a little charge dq over a little area dA, that will be equal to this constant sigma, which is nice. So we say, okay, this is great. I can write dq as sigma dA. So I can write this electric field as the integral, and I'm going to bring the 1 over 4 pi epsilon naught outside because it's a constant, z sigma dA all over z squared plus script r squared to the 3/2. Now this is an area integral, which means I will need to integrate over 2 dimensions. So I'm going to go ahead and add in my second integral here. So now this I can write as now sigma is a constant, so I'm going to bring it outside of my integral. 4 pi epsilon naught over 2 dimensions z dA over z squared plus r squared to the 3/2 power. But what is dA? Let's look at a small part of the area, so a little element really blown up. And at some distance, this is the z-axis coming out towards you. This is some distance away from the z-axis, script r, and it subtends some angle here, which I'm going to call d phi. So it's changing by some small angle, d phi. So this side is going to be if r changes. So if r changes a little bit, it's going to change by dr. And if phi changes by a little bit, I'll get this part, an arc length. And I remember that the arc length is r, the radius, times the angle. So r d phi. And when this section of charge is really, really small, then this is basically a rectangle. I've drawn it much larger than it really is. But these guys will be approximately parallel, and so will these two. So I can write my dA as simply dr times r d phi. I say, well, that's very nice. I can easily integrate over those. So now I can write my electric field EZ, which is the integral over all the EZs, which is sigma over 4 pi epsilon naught. I'm going to integrate over Z, now dA, which is script r, dr, d phi, over Z squared plus r squared to the 3/2. And so you're probably saying, what are we integrating over? Well, script r will start at 0 when the disk is right at the z-axis and integrate all the way out to the edge of the disk, because we want to include all of that charge. Let's say that that is a total distance r, big R. Big R is the radius that we're looking for. And then phi, we're going to integrate all the way around the disk. So it's going to start at 0 and then go to 2 pi. Very nice. Now I can do the phi integral really easily because there's no dependence on phi in my integrand, this term right here. So I can easily write this just as 2 pi sigma over 4 pi epsilon naught. And now the integral from 0 to big R of Z script r dr over Z squared plus r squared to the 3/2. Now, Z is a constant. In this case, I'm just some distance above the disk. So I can write this as now, oh, I noticed these guys canceled here, hooray. Sigma Z over 2 epsilon naught, integrate from 0 to big R, script r dr over Z squared plus r squared to the 3/2. Now, I want to do this integral, and I can do it in one of two ways. Either by doing trig substitution, which will be long and messy, or, and this is the preferred way, by simply looking it up in an integral table. So here comes my integral table, and I want to look for something that has the variable over a term where the variable is squared plus a constant squared to the 3/2 power. So I'm going to look in my section of the integral table with integrals involving things of x squared plus a squared square root, and so that sometimes goes to a power. I go to the next page. And here I find, finally, things that deal with 3/2. No variable up top, but the second one does have the variable dx, x squared, a squared to the 3/2. All right, so I've written this down, my integral here, and the integral table told me that this was just minus 1 over the square root of x squared plus a squared, square root of that mess. I'll say fantastic. Let's move on to the next page. All right. So now, if I make substitutions, I'm going to replace my x with a script r, and I'm going to replace a with z. That means that this is going to be minus 1 over the square root of r squared plus z squared. And I am integrating from 0 to r, which means I need to evaluate this term from 0 to r. Which means this is minus 1 over the square root of r squared plus z squared minus 1 over the square root of z squared. And that's just equal to 1. Or, sorry, 1 over z. So I can write this, there's a little bit more room here, as then minus, and the minus gives me positive 1 over z minus the 1 over the square root r squared plus z squared. All right, let's plug this into my equation. Ez, remember, is sigma z over 2 epsilon naught times this integral, which I now know is just 1 over z minus 1 over r squared plus z squared, square root. Now I'm going to multiply my z through, which means I can write this as sigma over 2 epsilon naught 1 minus z over r squared plus z squared. Good job. Now I know what the value of E is when I'm at z equals 0, when I'm right at the disk. So at z equals 0, Ez equals E sub m, E max really is what they're saying. So Em is equal to sigma over 2 epsilon naught 1 minus 0. So really, Em is just sigma over 2 epsilon naught. Let's say that's great. I want to find what the radius is, and if I look at the picture, the table, oops, here it comes. Notice that at half of z sub s is exactly, conveniently, the point where I have half the value of E max. So I can write this as the electric field at z equals zs over 2 is the point where it's equal to E max over 2. Oh, you can't see that. So sorry. There it is. So now I can write this part here as, let me just plug in zs over 2 into everything. So I get sigma over 2 epsilon naught times 1 minus zs over 2 over the square root, and bring this over a little bit more, of r squared plus zs over 2 squared is equal to Em, which is sigma over 2 epsilon naught over 2. So now let's do a little bit of simplification. Clearly the constants here cancel, which is nice. And I am able to write this as 2 minus zs over the square root of r squared plus zs over 2 quantity squared is equal to 1. So now I'm going to add this to both sides, subtract 1 from both sides. Let's line everybody up again here. All right. So I get 2 minus 1, that's just 1, equals ZS over the square root of R squared minus ZS over 2 squared. All right, so this really here is ZS squared 1 plus 1/4. That, of course, if I do my 4 over 4 here, that's 5/4. And then R is the square root of 5 over 2 times Z sub S. But I know what Z sub S is. They told me that in the problem. Z sub S is just 8 centimeters. So R is the square root of 5 over 2 times 8 centimeters. And if I plug all of this into my calculator, I find that R is equal to 6.9 centimeters. Good work. And this agrees. And that's the correct answer. So, we've seen that we can find how big the radius of the disk is by figuring out what the electric field is and how that depends on Z, and then comparing that with a graph and figuring out different points where we know values of E, and then finding ratios. So this is actually a very useful thing. All right, so I'll see you next time for more examples from Fundamentals of Physics 2 about electricity and magnetism.